So, good morning. Welcome to Krishna's classroom. We were looking at the concept of determinants in the past 5 lectures. Now, we are just halfway through generalizing it for the case, for the general case with the choice of n. Now, what we require as a tool when we consider the alternating n linear forms is some knowledge of what are called permutations and some of the important properties of permutations, namely the so-called parity. Now, we have got what are called odd permutations and even permutations. Therefore, before we straight away looking at the alternating n linear forms, we will first have a look at the concept of permutations and what we mean by the parity of the permutations. So, this is something out of the way and just required to understand some of the ideas that we pursue while considering the alternating and linear forms. Anyway, it is worthwhile looking at it. So, let us fix the notations. Let Sn denote the set of all integers 1 to n. Just a notation, not something very standard or anything. Now, what you call a permutation of order n is a 1-to-1, is a bijection on Sn. Now, we introduce the notation, define pi from as the identity permutation, namely by pi I equal to I this is the identity permutation. In fact, you see that you can easily see that there are n factorial bijections on Sn, and therefore, there are n factorial permutations on n symbols. Okay. So, let sigma and tau be 2 permutations on Sn. We know that the composition of sigma with tau, so sigma tau is a 1-to-1 onto map and therefore it is a permutation. This is defined as sigma of tau I. So, first tau acts on it and then sigma acts on it. So, it is a composition of sigma and tau that will give you the defined sigma tau for every I belonging to C. Now we have, you know that sigma inverse and tau inverse are defined. Now sigma inverse is defined. It exists first of all, because if sigma is a bijection, then sigma inverse is a bijection, is defined by sigma j equal to sigma I inverse I equal to j whenever I. That's the definition. Then you see that sigma inverse equal to sigma inverse sigma equal to pi. Therefore, so now let us denote by Pn, all permutations on Sn. Then Pn is a group with respect to the multiplication defined by the defined as the composition. Remark: in general, it is not a commutative group. Now we look at a special class of permutations, like we define what are called transpositions. Transpositions. Let be such that tau p equal to q, tau q equal to p, and tau of I equal to I whenever I is not equal to p q. Of course, we take p P not equal to q. Then tau is called a transposition. It simply says that for all I gets mapped to itself except P and Q, where P and Q are assumed to be different, and P gets mapped to Q and Q gets mapped to P. Okay, so you have of course P, Q. This is what you call a transposition, and clearly pi square equal to tau square pi, whenever tau is a transposition. Now we define another type of transformation of permutation, namely cycles. Choose P distinct integers between 1 to 1 and n. Say I1, I2, IP. Now, of course, P is less than or equal to n. Now define sigma ij equal to I j plus 1 for 1 and sigma IP equal to I1. Further, sigma I equal to I itself for I not equal to I1, I not equal to I2, that means only the effective changes take place only on these symbols, namely I1, I2, etc. In. So I1 gets mapped to I2, I2 gets mapped to I3 and so on. IP minus 1 gets mapped to IP and IP in turn gets mapped to I1. So it's actually you are representing them on a circle. So you have got I1, it goes to I2, I3, this is IP and this is minus 1. So you have this and IP gets mapped to I1. Now such a sigma is called a cycle. Cycle and is denoted by now this now has a meaning that I1 goes to I2, I2 goes to I3, etc. IP minus 1 goes to IP and IP in turn goes over to I1. Okay. Now this is called a p cycle. Now these are important class of permutation. Now we will look at we make some remark. See, here we have chosen I1, I2, etc., IP, and we have not said anything about it, namely that whether this is an ordered set of numbers or not. It is not, in fact. In fact, we do not assume it's important. So for instance, you can talk about 2, 1, 3, because if you write 2, 1, 3, it means 2 goes to 1, 1 goes to 3, and 3 goes to 2. This is the cycle that you have. And of course, we are not assuming 2 is less, obviously 2 is not less than 1. So we are not assuming that this kind of order relation is satisfied. So we want to make another remark, that is, all permutations one, 2, 3, 2, 3, 1 and 3, 1, 2. Represent the same cycle. Now we want to introduce what are called disjoint cycles. Define what are called disjoint cycles. We say that cycles say sigma JQ whenever if none of the i's are equal to the j's. That means this I1, I2, IP intersection J1, J2, JQ is empty. That is the set then you say that these are disjoint cycles. Now, one of the things that very quickly one can show that every permutation, okay, we make some remark. If are disjoint cycles, then sigma tau equal to tau sigma, that is they commute. I mean, that's very easy to, that is sigma and tau commute. That's easy to show. Now we have the following theorem. In fact, this is a string of theorems that eventually lead to what exactly we want. First thing that you have is that every permutation is a product of disjoint cycles, pairwise cycles. Now that is quite easy to prove, okay, it's not difficult at all, because suppose you look at the permutation. So let us take, I mean, it's a proof is very simple. You start with 1 and look at where it goes to. 1 goes to 3, say, then you write 3. So 1, 3, and then if 3 goes to 8, then you write 8 next, and so on. And eventually there is a stage where it comes back to 1. At most you will have to go through all these things. So you will get a cycle. Okay. Now you start with an integer which is not in this collection. Okay. And then do the same, and then you see that you can eventually exhaust all the integers. And some of them are, of course, 1 goes to 1, say k goes to k, and so on. So that's a different thing. Okay. Therefore, you can write down this as the product of 2 cycles, and of course they are disjoint. For example, if you take the permutation one, two, three, 4. Okay. Say let me choose 5 signals. Now you write 2, 5, 1, 3, 4. y. Okay, so let us see how we work on this. You see that you start with 1. 1 goes to 2, then 2 goes to 5. Now what happens next? 5 goes to 1, so 5 comes back to 1. So you have a cycle. Okay. Now you have another cycle. So 1, 2, 5 are there, 1, 2, 5 are there, so only 3 and 4 are there. So we start with 3, then 3 goes to 4 and 4 goes to 3. Therefore you see that it is the product of these two cycles and you have completely exhausted this. Okay, so you can write sigma as the product of two cycles. Okay, right? So that's the way in which you work it out, and the proof goes like this. So you start with 1, 2, 3, etc. n. You start with 1 goes to some I, and then you go to from see the image of I under sigma, and then put all those things together. Okay. So eventually you can exhaust all these things. The proof is given like this. I am not going into the proof, that is easy to work out. Now the next one is that theorem 2. Every cycle is a product of transpositions. It's a product of transpositions. These are some of the basic building blocks of the permutations, the transpositions. So we use the cycles and transpositions to read some properties of these. Okay, it's a product of transpositions. How to prove this? Friends, the proof is simple. For example, you look at this example will show you how to write this as transpositions. See that if you have, suppose I1, I2, I4 is a cycle, then you can write this as the product of I4, see I1, I4, I1, I3 and I1. You can check that the product of these transpositions is given by this. Now so the proof goes like this. So if you have a transposition 1, 2, 5, this you can break down as the product of 1, 5 with 1, 2. This is of course 3, 4. So there is a breakup of the and you can write this permutation as a product of transpositions. Now that's the consequence of this result. Okay, right? So in fact every permutation is a product of transpositions. So that's the next. Every permutation is a product of that's why I said it's a building block of permutation. every permutation can be written as the product of transpositions. And one of the important observations that you have to make is that the way in which you can break it up as a product of transpositions is not unique. So we will give an example. Remark: the way in which a permutation can be expressed as a transposition is not unique. So there is no unique way in which you can express a permutation as a product of transpositions. So we give some examples. First example, look at this: 1, 3. If you work this out, this will turn out to be 1, 2, 3. So also, if you take 1, 3, 1, 2, this is also equal to 1, 2, 3. Okay, there are different ways in which you can write down this. Now, for example, I have said that 1, 2, 3 is the same as 2, 3, 1, etc., etc. So you can write this out. Okay. Second example is that 1, 3, this you verify, 1, 4, 1, 2, 3, 4, 3, 2. This is equal to 1, 4, 1, 3, 1, 2. And that's equal to 1, 2. The cycle 1, 2, 3, 4 can be written out as in two different ways. Now this shows that then even the number of transpositions involved may be different. Okay, but there is a connection between the two numbers. So if a permutation can be written as the product of k transpositions, k1 transpositions, and also can be written as a product of k2 transpositions, then you see that if k1 is odd, then k2 is also odd. If k1 is even, then k2 is also even. So that in a way allows us to give a classification for the class of all permutations into two classes, namely odd permutations and even permutation. And this is the result that we need when we look at what are called alternating n-linear forms. So let us look at how these ideas emerge. Okay. So that is the one of the things that we observe. So we now look at a classification for permutations. So this is what is mentioned by what are called parity. Now let us give a sort of insight into how this whole idea comes about by taking an example, but it's quite easy to generalize this into the proof of these results. Okay, let f be a polynomial in 4 variables defined by f of into T2 minus T3, T2 minus T4 into T3 minus T4. You know how it comes. You start with T1, T1 minus T2, T1 minus T3, T1 minus T4, then T2 minus T3, T2 minus T4, and then T3 minus T4. So 6 factors come there. Okay, right. In general, f is the product of Ti minus Tj with now each permutation sigma belonging to P4, you can generalize to Pn, converts f into a new polynomial denoted by f defined by sigma f equal to the cycle T sigma 1, T sigma 2, T sigma 3, sorry, yeah, I didn't say it's cycle. So sigma f is defined as the f of f of T sigma 1, T sigma 2, T sigma 3 and T sigma 4. For example, if sigma is equal to, if tau is equal to 2, 4, then tau f at this is equal to f of what? T sigma 1, T tau 1, T tau 2, T tau 3, T tau 4, which is equal to f of tau 1 is 1, tau 2 is 4, tau 3 is 3 and tau 4 is equal to 2. So that's how you compute it, and you can write this in terms of that. So by changing the variables. Now one of the observations that you make is the following. We just write it up and then it will be clear how things come about. Okay. Now you see that this is equal to, this turns out to be T1 minus T4, T1 minus T3, T1 minus T2, T3 minus T4, T3, T4 minus T2, then T3 minus T2. That means, yeah, T1 minus T4, T1 minus T3, T1 minus T2, then T4 minus T3, T4 minus T2, T3 minus T2. That's the factors. And you can easily verify that this is equal to minus of f of it appears, at least in this particular case, the effect of working with sigma on f is to change its sign. Nothing happens except a change of sign. That you can easily check. This is because you see T1 minus T4 is there, and yeah, the definition T1 minus T4 is there, so no change. T1 minus T3 is there, that's also there. T1 minus T2 is there, that is also there. Then T4 minus T3 is there, but you have T3 minus T4, there is a change in sign. Then you have T4 minus T2, that's again there is a change in sign, and T2 minus T3 gets changed to T3 minus T2. Therefore, you see that there are three changes of sign, and consequently you get a minus sign appearing here. Okay, so this is the general argument that you are going to give, and now we will list it out. Now, if sigma is equal to 1, 3, 2, 4, then okay, so you have the following situation: 1, 2, 3, 4, and how it maps? 1, tau maps. See, first we are applying the map tau. So 1 goes to 1, 2 goes to 4, 3 goes to 3, 4 goes to 2. So this is the application of tau. Now we apply sigma. When you apply sigma, 1 goes to 3, 3 goes to 2, 2 goes to 4, and 4 goes to 1. So eventually this is applying next level sigma. So you see sigma tau is, therefore sigma tau works out to be 1 goes to 3, 2 goes to 1, 3 goes to 2, and 4 goes to 4. Therefore, this is essentially only these three symbols are permuted, 1, 2, 3. So that is the cycle that you get. So this turns out to be 1, 1, 1, 3, 3 goes to 2, and 2 goes to 1. Okay, that's it. So we make some observations and then use that to define the parity. So the first observation that we make is this: every permutation sigma the factors of sigma f are the same as that of f except for the sign and order. Except possibly that's the first observation. Okay. Therefore, what you get is this. The consequence is that sigma f, which implies minus sigma minus f or sigma f equal to f. These are the two possibilities. Now, sigma is called even sigma is called an even permutation if sigma f equal to f, and an odd permutation if so you see there are two. A permutation has a some property, namely it what you do is you observe what it does on f according to the operation that we have defined. So either sigma maps f to minus f or sigma maps f to plus f. These are the only possibility. One of the two possibilities can happen, and you see that accordingly this allows us to introduce or a classification for sigma, namely an odd permutation or an even permutation. Sigma is odd if sigma f is equal to minus f. Sigma is even if sigma f is equal to f. And we can introduce the following. We define signum notation. Now we write plus 1 if and sigma equal to minus 1 if. Now this we shall need for the next lecture, because this kind of classification is essential for our purpose. Right, the signum notation. Now the second observation that we make, if tau is a transposition, then tau of f minus f, that is signum of tau, signum of tau is a, now we are assuming tau is a transposition. So for every transposition its sign is equal to minus 1. Now the third one is going a bit into the details of that. So let me work through an example, but you can always do this. Tau be equal to 2, 4, the one that we have started with. Then every factor of f does not change. Only when this 2 or 4 are involved it changes. That is, T2 and T4 are involved, you see there is a change in the factor. Now let us analyze how this comes about. Every factor, so we make the observations, every factor remains the same f and sigma tau f whenever I is not equal to 2, 4, j not equal to 2, 4. So whenever I or j are both 1 and 3, the corresponding factor do not change at all. Okay, I mean that gives a pointer to the proof of the general case. See, it is enough to prove these things for cycles, because you see that every permutation is a product of cycles. It's one advantage that you have. Okay, so let me write what more comes out of it. What further observations come out. So every factor of f containing only one of P4 come in pairs. How does it come? See, if you have a factor, for example, you have T2 minus T3 gets changed to T4 minus T3. Similarly, T1 minus T2 gets changed to T4. And T3 minus T4 T4, yes. And T3 minus T4 gets changed to T4 minus T3. So these two just appear in pairs, and this one just changes its sign. Therefore, each such factor goes to the other except possibly that sign changes. If sign of one factor changes, then the sign of the pair also changes. So the sign changes together. So if one of the factors remain plus, the other remain unchanged, then the other one also remain unchanged. But on the other hand, for example, here T2 minus T3 goes to T4 minus T3. So you have T1 minus T2 goes to T1 minus T4. T2 minus T3 goes to T4 minus. So there is a change of sign. So here T1 minus T2 goes to T1 minus T4. Okay. So there is no change in sign here. But what are the factors that can come? T2 minus T3. So if you analyze this, you see that if those which occur in pairs, so you have T2 minus T3 and you have T3 minus T4. Okay. So look at that, how the changes take place. That's what I mean. So each such, if sign of one factor changes, its sign, then the sign of the pair also changes. For example, just explain this. If the factor contains both 2 and 4 which appear in the transposition, then you see that the factor remains the same except for the sign. That means T2 minus T4 goes to T tau 2 minus T tau 4, which is T4 minus T2. So there is a change in sign. Okay. Therefore, you see that tau f of and this is essentially therefore that's what we will do. Now we make a third observation. If are permutations, then you can show that sigma tau that is the definition, and consequently sigma tau even whenever both sigma same sign either they are both plus or they are both minus. Okay, now this is what that is same parity. Okay. So sigma tau is even if signum of that means both are the same parity. Otherwise, what happens? You have a change in sign. Okay? Right. So, one of the outcomes of this is that we have seen that every permutation can be written as the product of transpositions. So how many, although the representation, such a representation is not unique, but we can say something about the parity and connect it up into the number of factors or number of what you call transpositions that appear in the representation. Hence, the product of a set of transpositions is even if and only if the number of factors transpositions is even, because you see that the transposition has its signum -1, therefore the product is +1 if and only if the number of transpositions is even. Okay. Otherwise, of course, this is odd. It is odd if and only if number of transpositions. We also make one more observation. Suppose you have a p cycle. Suppose consider IP. Then this can be written as I minus IP, I minus IP minus 1, I1 minus I2. Okay. So we observe that, okay, this comma. I minus I1. So it's a product of transpositions. So the effect of each transposition is to change the sign of the sign of f. So this is SS, this has parity -1. Each one of this has parity -1. So if this cycle is even, so a p cycle is even, if and only if the number of in any of its representation Now, how many such representations are there? There are p minus 1. Therefore, you also observe that this is equal to, so here you see that the അവിടെ ചോദിക്കും even or odd if and only if its product, it is a product of odd number of transpositions. So that's the result that you have. Okay, so these are some of the observations that we make. Now you also observe that if you have for a p cycle, odd or even if and only if p is even or odd. The reason is this. See, if you have a p cycle, the number of transpositions that appears in this representation are p minus 1. Okay, and therefore signum of I1 IP equal to how many such products are there? There are p minus 1 products. Okay, so this is equal to minus 1 to the power p minus 1. Okay, right? Therefore, you see, you get this relation. So if it is odd, then see, this is equal to minus 1 if p minus 1 is odd, that is p is even. This is equal to plus 1 if p minus 1 is what you call even, sorry, is odd, right? sorry, p minus 1 is even, which means that p is odd. So this relation follows from there. Therefore we have the product of two even permutations the product of two odd permutations is even. The product of an odd permutation and an even permutation is odd. So these are the final outcome that you have, and in fact what you can show is that a set of all even permutations form a subgroup of Pn, with, of course, note that by that is the identity map is taken as an even permutation. Now these are some of the outcomes of this. Now you can devise the proof for all these results by, in the general scenario, by almost mimicking what we did in the case of say the case of 1, 2, 3, 4. Okay. Now what we want to conclude is this. See, it comes like this. Every permutation is the product of disjoint cycles, and each disjoint cycle is a product of transpositions. Therefore every permutation is a product of transpositions. So you see that if in one representation, I mean, I said that the representation of a permutation as a product of transpositions is not unique. Okay, right? Therefore if you have two different representations for the same permutation, then you see that the number of factors that appear in its representation as product of transpositions is going to be either even in both cases or odd in both cases. Okay, with these remarks, let me stop it here. Now we will take up what is called alternating and linear forms in my next lecture. Thank you very much.